So I am realizing that I'm not actually using the delta grad W's and delta grad B's from this backprop. So I went back to this formula here to try to figure out how is this supposed to fit together. So here's how I think it works. I think this term here, which is the gradient from a single example, a single test case, is what's being called delta grad W and delta grad B. So it's the grad from a single example. The sum over j's here is the gradient for all the examples in the mini batch, is the sum of the delta grads for all the examples in the mini batch. So I'm going to rewrite this to work like that. So these are sums of gradients in the mini batch. So grad of W of I plus equals delta grad of W of I. Grad of B of I plus equals delta grad of B of I. So these grads, which is this term here, start at 0. Then we add the contribution from each example in the mini batch. Then we multiply this thing by eta over m and subtract that from what the weights used to be. So yeah, this is the way that makes sense to me now. And then actually use this as backprop. So from here, last time I said we would decide whether we would just copy the backpropagation code and get it running and then try to understand it later. I'm gonna say we're not gonna do that. So I'm just gonna keep reading until I understand what the backpropagation code is supposed to be doing. And then I'll implement it myself without using their implementation. So yeah, let's get back to it. This invokes something called the backpropagation algorithm, which is a fast way of computing the gradient of the cost function. So update mini batch works by simply computing these gradients for every training example in the mini batch and then updating self.weights and self.biases appropriately. I'm not going to show the code for self.backprop right now. We'll study how backpropagation works in the next chapter, including the code for self.backprop. For now, just assume that it behaves as claimed, returning the appropriate gradient of the cost function associated to the training example x. Let's look at the full program, including the documentation strings, which I omitted above. Okay, we read this last time. So we're gonna skip over this. Backprop is implemented. We don't know how to do that yet. Evaluate we could just do. This is just checking how it does. But we're gonna leave that for when we're actually running the code. How well does the program recognize handwritten digits? Well, let's start by loading in the MNIST data. I'll do this using a little helper program, mnistloader.py. To be described below. We execute the following commands in a Python shell. Import mnistloader, training data, validation, test data equals mnistloader.loadDataWrapper. So we implemented something similar to this. We can instantiate a data loader and then call data.training, data.validation, data.testing to get the appropriate pieces of it. After loading the MNIST data, we'll set up a network with 30 hidden neurons. We do this after importing the Python program listed above, which is named network. Okay, we can do this. So let's make a main.py. It's going to import, or from data loader import data loader, from network import network, net equals network dot, or just network. We're going to do the same thing they're doing. So there's this many pixels in the input images. Let's do 30 hidden neurons and 10 output. Then we do net.train. And this needs epochs, mini batch size, ADA, and training data. So epochs equals, let's say 10. Mini batch size, we'll say 100. ADA, 0.1. And training data is data.training. Data.training. And I never instantiated data. So data equals data loader, data.load. Okay. So then I guess after training, what we would want to do is net.evaluate. Data.validation. How would we call it? Validate then. If you train on training data, you validate on validation data. And we didn't implement a validate, so let's do that right now. Def validate self validation data equals, or it just is, and it has a complicated type signature, so we're not going to implement it. But how do you do this? You do you apply it on each example. So for x, y in validation data. X is what is the input, and then we're trying to check if that's equal to y, if our output is equal to y. But y is going to be a actually, okay, a few problems. Validation data is a tuple of examples and labels, so we want to zip them together. And why is this underlined? So let's say what this is. Actually, can I just define in data loader? Let's just give it, let's export a type. Data. Well, it's actually images, image, and label, right? So, type image equals list of int. Type label equals int. So this returns a tuple of Wait, is it a list of events or is it just a list of events? Is an image 28 by 28 or is it a 784? I guess we need to find out. Give me the first image. Python data loader. Or yeah, give me the actual first image. I guess give me the length of that. Ah, okay. So this is just a list of ints. So type data is going to be, and I can just add this here, data is a tuple of list of image and list of label. So training returns data, validation returns data, and testing returns data. Now if we go over to network test data, this is a type list data. Oh wait, no, it's just type data. Equals none. Data or none. I have to import that from data loader, import data. But that's actually an inconvenient way of doing it. So I think I actually want one data point. Instead of returning the tuples and you have to zip them when you use them, why don't we zip them ourselves? So data is going to be a list of tuple of image and label. Which means this needs to return the zip of it, cast it into a list. Yeah. So an image is a list of ints, a label is just an int, data is a list of image label pairs. Okay. Network. And training data is data. Mini batches are correctly typed now, except that X is right now not a ND array. Which is a problem. So image should be an from or import numpy as np np.ndArray. So these should be np.array image or image in images. And all images should be a list of np.ndArray. Okay, same for test images. Okay. I think our types make sense now. So now if we go back to main, yeah, we can pass in training data directly. We should be able to pass in validation data directly. Cannot access attribute validate. That's because I haven't implemented it yet, have I? Well, I have though. Why is it? Okay, so I don't need the zip anymore. Apply returns a ND array, and y is just an int. So here's where I want to do the argmax thing. np.argmax. Let's just test that. Python. Import numpy as np. np.argmax of 1, 2, 3, 4, 5, 3, 1. It returns 3. And if this were an ND array, np.array. Oh wait, 3 is not. Wait, actually, yes. What I want is the index of the maximum. Is that what argmax does? So if this were 3, 2, and this one were 9. Oh, okay. So that is what argmax does. So this is what I want. Validate returns percentage. Percentage equals 0. And it goes up by percentage plus equals this over length of validation data. Return percentage. So I think this works. Basically, this will be equal to 1 when the example is successful. If they're all 1, then you'll get len of validation data over len of validation data, so the percentage will be 1.0. If they're all 0, you get 0%, and if they're in between, you get whatever percentage is, right? So you add 1 n to the percentage for each n that's correct. For each of n that is correct. So I think that's what validate does. I don't know why it's saying that. Is it just like, oh, okay, it was just like out of date. Percent equals this, percent. Obviously this is not going to work because we haven't implemented backprop yet, but we're ready to implement backprop now. Python main. So it takes a bit to load the data. And then we fail when we try to do a backprop. Good. Okay. Finally, we'll use stochastic gradient descent to learn from the MNIST training data over 30 epochs. So sure, why don't we do 30 epochs? Batch size of 10. Learning rate of 3.0. test data for some reason instead of training data, but I'm not going to switch that. Note that if you're running the code as you read along, it will take some time to execute. For a typical machine as of 2015, it will likely take a few minutes to run. I suggest you set things running, continue to read, and periodically check the output from the code. If you're in a rush, you can speed things up by decreasing the number of epochs or decreasing the number of hidden neurons. Yeah, let's decrease the number of epochs, even though we're not running it right now. Or by only using part of the training data. Note that production code would be much, much faster. These Python scripts are intended to help you understand how neural nets work, not to be high-performance code. And of course, once we've trained a network, it can be very quick. It can be run very quickly indeed on almost any computing platform. For example, once we've learned a good set of weights and biases for our network, it can easily be ported to run in JavaScript in a web browser or as a native app on a mobile device. In any case, here is a partial transcript of the output of one training run of the neural network. The transcript shows the number of test images correctly recognized by the neural network after each epoch of training. As you can see, after just a single epoch, this has reached 9,129 out of 10,000, and the number continues to grow. That is, the trained network gives us a classification rate of around 95%, 95.42% at its peak, epoch 28. That's quite encouraging as a first attempt. I should warn you, however, that if you run the code, then your results are not necessarily going to be quite the same as mine. Since we'll be initializing our network using different random weights and biases, to generate results in this chapter, I've taken best of 3 runs. Let's rerun the above experiment, changing the number of hidden neurons to 100. As was the case earlier, if you're running the code as you read along, you should be warned that it takes quite a while to execute. On my machine, this experiment takes tens of seconds for each training epoch. So it's wise to continue reading in parallel while the code executes. Changing hidden neurons to be more. Sure enough, this improves the results to 96.59%, at least in this case, using more hidden neurons to help us get better results. Footnote, reader feedback indicates quite some variation in results from this experiment, and some training runs give results quite a bit worse. Using the techniques introduced in Chapter 3 will greatly reduce the variation in performance across different training runs for our network. Of course, to obtain these accuracies, I had to make specific choices for the number of epochs of training. The mini-batch size and the learning rate, eta. As mentioned above, these are known as hyperparameters for a neural network, in order to distinguish them from the parameters, weights and biases, learned by our learning algorithm. If we choose our hyperparameters poorly, we can get bad results. Suppose, for example, that we chose the learning rate to be eta equals 0.001. Then it learns slower. However, you can see that the performance of the network is getting slowly better over time. That suggests increasing the learning rate, say to eta equals 0.01. If we do that, we get better results, which suggests increasing the learning rate again. If making a change improves things, try doing more. If we do that several times over, we'll end up with a learning rate of something like eta equals 1.0, and perhaps fine-tuned to 3.0, which is close to our earlier experiments. So even though we initially made a poor choice of hyperparameters, we at least got enough information to help us improve our choice of hyperparameters. In general, debugging a neural network can be challenging. This is especially true when the initial choice of hyperparameters produces results no better than random noise. Suppose we try the successful 30 hidden neuron network architecture from earlier, but with learning rate changed to eta equals 100. Learning rate 100. At this point, we've actually gone too far, and the learning rate is too high. It's not learning anything, and eventually it gets slightly worse. Now imagine that we were coming to this problem for the first time. Of course, we know from our earlier experiments that the right thing to do is to decrease the learning rate, but if we were coming to this problem for the first time, then there wouldn't be much in the output to guide us on what to do. We might worry not only about the learning rate, but about every other aspect of our neural network. We might wonder if we've initialized the weights and biases in a way that makes it hard for the network to learn. Or maybe we don't have enough training data to get meaningful learning. Perhaps we haven't run for enough epochs, or maybe it's impossible for a neural network with this architecture to learn to recognize handwritten digits. Maybe the learning rate is too low, or maybe the learning rate is too high. Maybe when you're coming to a problem for the first time, you're not always sure. The lesson to take away from this is that debugging a neural network is not trivial, and as for ordinary programming, there's an art to it. You need to learn the art of debugging in order to get good results from neural networks. More generally, we need to develop heuristics for choosing good hyperparameters and good architecture. We'll discuss all these at length through the book, including how I chose the hyperparameters above. Exercise. Try creating a network with just 2 layers, an input and an output layer, no hidden layer, with 784 and 10 neurons respectively. Train the network using stochastic gradient descent. What classification accuracy can you achieve? We'll have to come back to this because we haven't actually run the code yet, because we're being stubborn. I'm being stubborn, and I want to write it myself. I don't just want to copy it. So here's a to-do for later. Earlier, I skipped over the details of how the MNIST data is loaded. It's pretty straightforward. For completeness, here's the code. The data structures used to store the MNIST data are described in the documentation strings. It's straightforward stuff, tuples and lists of NumPy ND array objects. Think of them as vectors if you're not familiar with ND array. Okay, so we kind of did, I mean, we're using a library that loads it for us. And then I'm changing it to be the right thing. Like I'm converting it to ND arrays, I'm zipping the lists. So I'm already doing some of this. Oh, you know what? I'm doing all of this because they're also cheating because they're just pickling they're just unpickling the test data. So they already processed it and then pickled it and then uploaded the pickled version. Or is that true? Or is that just, we've got load data and load data wrapper. But yeah, they start by loading the pickled data, and then they convert it into NumPy arrays. And I'm noticing I forgot that I have to reshape the arrays to be n by 1. I did that somewhere though. Where did I do that? I think I did that in Sigmoid. No. Did I do it in network? Where did I do that? I remember having to reshape things. I'm doing apply it on an NP, or yeah, on a NumPy array, which is not going to work unless you, oh. No, I'm just, it looks like I'm not handling that in the Sigmoid, so that must have been in network. Apply. I'm not doing it here either. Oh, here I'm doing it. I'm transposing it. Okay, but that's not going to work if I'm loading, when I'm loading the data. So let's add to our data loader the reshaping thing. Which means I need to do something like this, or image in PR images. Append the image, but don't just append the image. I also want to reshape it. the way they're doing it here, does np.reshape, I was doing .reshape on the image, so I was doing like image equals this, image.reshape to be image.shape of 0 and 1, and then append image. Let's make a helper function here, def toArray, which is going to take a list of ints. Image dot returns an np.nbarray, which I can never spell right on the first try. This just does I or in dot rect equals np dot array image ret dot reshape to be ret dot shape of 0, comma 1, return ret. And then here I can go back to doing them in bulk like this. Training images, you call toArray on the image. Okay. Yeah, and then there's zipping the inputs with the results. Oh, they're vectorizing the result. I'm just leaving it as an integer. I don't think that matters, because I guess it's gonna matter at some point. At some point we'll have to vectorize the result. When do we use y? We don't actually use it yet, right? We just pass it into backprop, and then in the validation we're doing it correctly. So yeah, they're doing it a different way, but that doesn't matter. Okay. I said above that our program gets pretty good results. What does that mean? Good compared to what? It's informative to have some simple non-neural network baseline tests to compare against to understand what it means to perform well. The simplest baseline of all, of course, is to randomly guess the digit. That'll be right about 10% of the time. We're doing much better than that. What about a less trivial baseline? Let's try an extremely simple idea. We'll look at how dark an image is. For instance, an image of a 2 will typically be quite a bit darker than an image of a 1, just because more pixels are blacked out, as the following example illustrates. This suggests that the training data to compute average darkness for each digit, 0, 1, 2, etc., 9, when presented with a new image, we compute how dark the image is, and then guess that it's whichever digit has the closest average. This is a simple procedure, and is easy to code up, so I won't explicitly write out the code. If you're interested, it's in the GitHub repository. But it's a big improvement over random guessing, getting 2,225 out of the 10,000 test images correct, i.e. 22.25% accuracy. It's not difficult to find other ideas which achieve accuracies in the 20 to 50% range. If you work a bit harder, you can get up over 50%. But to get much higher accuracies, it helps to use established machine learning algorithms. Let's try using one of the best known algorithms, the support vector machine, or SVM. If you're not familiar with SVMs, not to worry, we're not going to need to understand the details of how SVMs work. Instead, we'll use a Python library called scikit-learn, which provides a simple Python interface to a fast C-based library for SVMs, known as libsvm. I'm not going to do this, I'm just going to read what he has to say. My goal is to write a large language model, so I'm only doing stuff that helps me on that path. If we run scikit-learn's SVM classifier using the default settings, then it gets 9,435 of 10,000 test images correct. The code is available here. That's a big improvement over our naive approach of classifying an image based on how dark it is. Indeed, it means that the SVM is performing roughly as well as our neural networks, just a little worse. In later chapters, we'll introduce new techniques that enable us to improve our neural networks so that they perform much better than the SVM. That's not the end of the story, however. The 9,435 of 10,000 results is for scikit-learn's default settings for SVMs. SVMs have a number of tunable parameters, and it's possible to search for parameters which improve this out-of-the-box performance. I won't explicitly do this search, but instead refer you to this blog post by Andreas Mueller, if you'd like to know more. Mueller shows that with some work optimizing the SVM's parameters, it's possible to get the performance up to 98.5% accuracy. In other words, a well-tuned SVM only makes an error on about 1 digit in 70. That's pretty good. Can neural networks do better? In fact, they can. At present, well-designed neural networks outperform every other technique for solving MNIST, including SVMs. Current 2013 record is classifying 9,979 out of 10,000 images correctly. This was done by Li Wan, Matthew Zeiler, Sixin Zhang, Yan LeCun, and Rob Fergus. We'll see most of the techniques they use later in the book. At that level of performance, it's close to human equivalent and is arguably better, since quite a few of the MNIST images are difficult even for humans to recognize with confidence. For example, I don't know what's going on with most of these. Some of these are clearly not digits. I trust you'll agree that those are tough to classify. With images like these in the MNIST dataset, it's remarkable that neural networks can accurately classify all but 21 of the 10,000 test images. Usually when programming, we believe that solving a complicated problem like recognizing the MNIST digits requires a sophisticated algorithm. But even the neural networks in the Wan et al. Paper mentioned involve quite simple algorithms, variation on the algorithm we've seen in this chapter. All the complexity is learned automatically from the training data. In some sense, the moral of both our results and those in the more sophisticated papers is that for some problems, sophisticated algorithms are not as good as simple learning algorithms plus good training data. Towards deep learning. While our neural network gives impressive performance, that performance is somewhat mysterious. The weights and biases in the network were discovered automatically, and that means we don't immediately have an explanation of how the network does what it does. Can we find some way to understand the principles by which our network is classifying handwritten digits, and given such principles, can we do better? To put these questions more starkly, suppose that a few decades hence, neural networks lead to artificial intelligence, AI. Will we understand how such intelligent networks work? Perhaps the networks will be opaque to us. The weights and biases we won't understand, because they've been learned automatically. In the early days of AI research, people hoped that the effort to build an AI would also help us understand the principles behind intelligence, and maybe the functioning of the human brain, but perhaps the outcome will be that we end up understanding neither the brain nor how artificial intelligence works. To address these questions, let's think back to the interpretation of artificial neurons that I gave at the start of the chapter, as a means of weighing evidence. Suppose we want to determine whether an image shows a human face or not. We could attack the problem the same way we attacked handwriting recognition, by using the pixels in the image as input to our neural network, with the output from the neural network, a single neuron indicating either yes it's a face or no it's not a face. Let's suppose we do this, but that we're not using a learning algorithm. Instead, we're going to try to design a network by hand, choosing appropriate weights and biases. How might we go about it? Forgetting neural networks entirely for a moment, a heuristic we can use is to decompose the problem into subproblems. Does the image have an eye in the top left? Does it have an eye in the top right? Does it have a nose in the middle? Does it have a mouth in the bottom middle? Is there hair on top? And so on. If the answer to several of these questions are yes, or even just probably yes, then we'd conclude that the image is likely to be a face. Conversely, if the answers to most of the questions are no, then the image probably isn't a face. Of course, this is just a rough heuristic, and it suffers from many deficiencies. Maybe the person is bald, and so they have no hair. Maybe we can only see part of the face, or the face is at an angle, or some of the facial features are obscured. Still, the heuristic suggests that if we can solve the subproblems using neural networks, then perhaps we can build a neural network for face detection by combining the networks for the subproblems. Here's a possible architecture with rectangles denoting the subnetworks. Note that this isn't intended as a realistic approach to solving the face detection problem. Rather, it's to help us build intuition about how networks function. Here's the architecture. Input layer, image pixels. These go to a bunch of subnetworks for is there an eye in the top left, eye in the top right, etc., and that goes to a single output neuron that says, is this a face? It's also plausible that the subnetworks can be decomposed. Suppose we're considering the question, is there an eye in the top left? This can be decomposed into questions such as, is there an eyebrow? Are there eyelashes? Is there an iris? And so on. Of course, these questions really include positional information as well. Is the eyebrow in the top left and above the iris? That kind of thing. So let's keep it simple. The network that answers the question, is there an eye in the top left, can now be decomposed. Eyebrow, eyelash, iris. Those questions too can be broken down further and further through multiple layers. Ultimately, we'll be working with subnetworks that answer questions so simple they can easily be answered at the level of single pixels. Those questions might, for example, be about the presence or absence of very simple shapes at particular points in the image. Such questions can be answered by single neurons connected to the raw pixels in the image. The end result is a network which breaks down a very complicated question. Does the image show a face or not? Very simple questions answerable at the level of single pixels. It does this through a series of many layers, with each layer answering very simple and specific questions about the image, and later layers building up a hierarchy of even more complex and abstract concepts. Networks with this kind of many-layer structure, two or more hidden layers, are called deep neural networks. Of course, I haven't said how to do this recursive decomposition into subnetworks. It certainly isn't practical to hand design the weights and biases in the network. Instead, we'll use learning algorithms so that the network can automatically learn the weights and biases, and thus the hierarchy of concepts from training data. Researchers in the 1980s and 1990s tried using stochastic gradient descent and backpropagation to train deep networks. Unfortunately, except for a few special architectures, they didn't have much luck. The networks would learn, but very slowly, and in practice, often too slowly to be useful. Since 2006, a set of techniques has been developed that enable learning in deep neural nets. These deep learning techniques are based on stochastic gradient descent and backpropagation, but also could introduce new ideas. These techniques have enabled much deeper and larger networks to be trained. People now routinely train networks with 5 to 10 hidden layers, and it turns out that these perform far better on many problems than shallow neural networks, i.e. networks with just a single hidden layer. The reason, of course, is the ability of deep nets to build up a complex hierarchy of concepts. It's a bit like the way conventional programming languages use modular design and ideas about abstraction to enable the creation of complex computer programs. Comparing a deep neural network to a shallow network is a bit like comparing a programming language with the ability to make function calls to a stripped-down language with no ability to make such calls. Abstraction takes a different form in neural networks than it does in conventional programming, but it's just as important. Okay. End of chapter 1. Let's go to chapter 2. Learn about backpropagation, and hopefully we can actually run the neural network. Alright, let's get going. In the last chapter, we saw how neural networks can learn their weights and biases using gradient descent algorithms. There was, however, a gap in our explanation. We didn't discuss how to compute the gradient of the cost function. That's quite a gap. It sure is, because of that, I haven't even run the code yet. Also, this is not related, but I just realized my backprop signature is wrong. No. Wait. Yes. This should be a tuple. It returns a tuple. The tuple is the W's and the P's, but then it's a list of W's and P's. So this should be a tuple of a list of this. There's only one in here, right? The tuple is that there's two lists. Okay. In this chapter, I'll explain a fast algorithm for computing such gradients, an algorithm known as backpropagation. The backpropagation algorithm was originally introduced in the 1970s, but its importance wasn't fully appreciated until a famous 1986 paper by David Rubenhall, Jeffrey Hinton, and Ronald Williams. That paper describes several neural networks where backpropagation works far faster than earlier approaches to learning, making it possible to use neural nets to solve problems which had previously been insoluble. Today, the backpropagation backpropagation algorithm is the workhorse of learning in neural networks. This chapter is more mathematically involved than the rest of the book. If you're not crazy about mathematics, you may be tempted to skip the chapter and to treat backpropagation as a black box whose details you're willing to ignore. Why take the time to study those details? The reason, of course, is understanding. At the heart of backpropagation is an expression for the partial derivative of c with respect to w of the cost function c with respect to any weight w or bias b in the network. The expression tells us how quickly the cost changes when we change the weights and biases. And while the expression is somewhat complex, it also has a beauty to it, with each element having a natural, intuitive explanation. And so, backpropagation isn't just a fast algorithm for learning, it actually gives us detailed insights into how changing the weights and biases changes the overall behavior of the network. That's well worth studying in detail. With that said, if you want to skim the chapter or jump straight to the next chapter, that's fine. I've written the rest of the book to be accessible even if you treat backpropagation as a black box. There are, of course, points later in the book where I refer back to results from this chapter, but at those points you should still be able to understand the main conclusions even if you don't follow all the reasoning. Warm-up, a fast matrix-based approach to computing the output from a neural network. Before discussing backpropagation, let's warm up with a fast matrix-based algorithm to compute the output from a neural network. We actually already briefly saw this algorithm near the end of the last chapter, but I described it quickly, so it's worth revisiting in detail. In particular, this is a good way of getting comfortable with the notation used in backpropagation in a familiar context. Let's begin with a notation which lets us refer to the weights in the network in an unambiguous way. We'll use WLJK to denote the weight for the connection from the kth neuron in the L-1th layer to the jth neuron in the Lth layer. So for example, the diagram below shows the weight on a connection from the 4th neuron in the 2nd layer to the 2nd neuron in the 3rd layer of a network. W3, so 3, the superscript is the layer, so we're starting on layer 3. Then we're talking about a connection from L-1 to L, so somewhere in this blob of thing. Then it's J is in the Lth layer and K is in the layer before. So J is 2 and K is 4. This notation is cumbersome at first and it does take some work to master, but with a little effort, you'll find the notation becomes easy and natural. One quirk of the notation is the ordering of the J and K indices. You might think that it makes more sense to use J to refer to the input neuron and K to the output neuron, not vice versa, as is actually done. I'll explain the reason for this quirk below. We use a simpler notation for the network's biases and activations. Explicitly, we use BLJ for the bias of the jth neuron in the Lth layer, and we use ALJ for the activation of the jth neuron in the Lth layer. The following diagram shows examples of these notations in use. This is the activation of the first neuron in the 3rd layer. This is the bias of the 3rd neuron in the 2nd layer. With these notations, the activation ALJ of the jth neuron in the Lth layer is related to the activations in the L-1th layer by the equation, compare equation 4, and surrounding discussion in the last chapter. So ALJ is equal to sigmoid of this term, which we call Z, but the way you compute Z is with the dot product of W and the output of the last layer. My weights, the weights of my neuron and the output of the last layer, plus my bias. Where the sum is over all neurons K in the L-1th layer. To rewrite this expression in the matrix form, we define a weight matrix WL for each layer L. The entries of the weight matrix WL are just the weights connecting to the Lth layer of the neuron. That is, the entry in the jth row and kth column is WLJK. Similarly, for each layer L, we define a bias vector BL. You can probably guess how this works. The components of the bias vector are just the values b, l, j, one component for each neuron in the L layer. And finally, we define an activation vector, AL, whose components are the activations ALJ. The last ingredient we need to rewrite 23 in a matrix form is the idea of vectorizing a function such as sigmoid. We met vectorization briefly in the last chapter, but to recap, the idea is that we want to apply a function such as sigmoid to every element in the vector v. We use the obvious notation sigmoid of v to denote this kind of element-wise application of the function. That is, the components of sigmoid of v are just sigmoid of vj equals sigmoid of vj. As an example, if we have the function f of x equals x squared, then the vectorized form of f has the effect where you're just squaring each element. That is, the vectorized f just squares every element of the vector. With these notations in mind, equation 23 can be rewritten in the beautiful and compact vectorized form AL, so activation of the activation of all the neurons in the L layer is equal to sigmoid of, and then this is going to be a vector, the matrix W for that layer, matrix multiplied with the activation of the previous layer plus the vector of biases of this layer. This expression gives us a much more global way of thinking about how the activations in one layer relate to the activations in the previous layer. We just apply the weight matrix to the activations, then add the bias vector. And finally apply the sigmoid function. Let's read the footnote here. By the way, it's this expression that motivates the quirk in the WLJK notation mentioned earlier. If we used J to index the input neuron and K to index the output neuron, then we'd need to replace the weight matrix in equation 25 by the transpose of the weight matrix. That's a small change but annoying, and we'd lose the easy simplicity of saying and thinking, apply the weight matrix to the activation. That global view is often easier and more succinct and involves fewer indices than the neuron by neuron view we've been taking to now. Think of it as a way of escaping index hell while remaining precise about what's going on. The expression is also useful in practice because most matrix libraries provide fast ways of implementing matrix multiplication, vector addition, and vectorization. Indeed, the code in the last chapter made implicit use of this expression to compute the behavior of the network. When using equation 25 to compute A of L, we compute the intermediate quantity Z of L is defined as W matrix multiplied by A of the last layer plus bias of this layer along the way. This quantity turns out to be useful enough to be worth naming. We call Z of L the weighted input to the neurons in layer L. We'll make considerable use of the weighted input Z of L, or ZL, however you want to say it, later in the chapter. Equation 25 is sometimes written in terms of the weighted input as activation of the Lth layer equals sigmoid of the weighted input to the Lth layer. It's also worth noting that ZL has components ZL equals sum over k of WLJK times AL minus 1k plus BLJ. That is, ZLJ is just the weighted input to the activation function for neuron J in layer L. All very straightforward so far. We haven't learned anything new yet. We're just repeating stuff, using new notation for it. The two assumptions we need about the cost function. The goal of backpropagation is to compute the partial derivatives, derivative of c with respect to w, and derivative of c with respect to b of the cost function c with respect to any weight w or bias b in the network. For backpropagation, the work we need to make two main... For backpropagation to work, we need to make two main assumptions about the form of the cost function. Before stating those assumptions, though, it's useful to have an example cost function in mind. We'll use the quadratic cost function from last chapter, equation 6. In the notation of the last section, the quadratic cost has the form c equals 1 over 2n times the sum over x of the square of the distances between what we got and what we wanted. Where n is the total number of training examples, the sum is over individual training examples, x, y equals y of x, is the corresponding desired output, L denotes the number of layers in the network, and A of uppercase L equals A of uppercase L of x is the vector of activations output from the network when x is input. Okay, so what assumptions do we need to make about our cost function, C, in order that backpropagation can be applied? The first assumption we need is that the cost function could be written as an average, C equals 1 over n times the sum of the C's over cost function C of x for individual training examples of x. This is the case for the quadratic cost function, where the cost for a single training example is C of x equals 1/2 times the square of the distance between y and the final activation layer. This assumption will also hold true for all the other cost functions we'll use in this book. Alright, let me try to understand what's saying here. The assumption is that the cost function can be written as an average over cost functions for individual training examples. And this is the case for quadratic cost function. What would it not be the case for? How could the cost function not be an average of costs for individual examples? I guess if the cost function was like, which digit is farthest away, then it's like a max or a min, and so it's the overall max is not the average of the max of each individual one. It's the max of each individual one. Okay. The reason we need this assumption is because what backpropagation actually lets us do is compute the partial derivatives, derivative of Cx with respect to W, derivative of Cx with respect to B for a single training example. We then recover C, derivative of C with respect to W, and derivative of C with respect to B by averaging over training examples. In fact, with this assumption in mind, we'll suppose the training example X has been fixed and drop the X subscript, writing the cost Cx as C. We'll eventually put the X back in, but for now it's a notational nuisance that is better left implicit. The second assumption we make about the cost is that it can be written as a function of the outputs from the neural network. So the cost of the output activation. For example, the quadratic cost function satisfies this requirement, since the quadratic cost for a single training example x may be written as C equals 1 over distance between y and a, L, which is equal to square of that distance, which is equal to which is equal to the sum of the distances between each component in the vector. Because the definition of distance is you sum the squares of the components and then you take a square root. So if you're taking the square of the distance, then you're just summing the squares of the components. And thus is a function of the output activations. Of course, this cost function also depends on the desired output y, and you may wonder why we're not regarding the cost also as a function of y. Remember though that the input training example x is fixed, and so the output y is also a fixed parameter. In particular, it's not something we can modify by changing the weights and biases in any way, i.e. it's not something which the neural network learns. And so it makes sense to regard C as a function of the output activations A of L, output activation AL alone, with Y merely a parameter that helps define that function. Okay. So C is a function of the output activations. The cost is a function of the output. And the fact that we're measuring it as how far away it is from y, you can just think of y as a constant. So for any given input, C is a function of its output. Okay. The Hadamard product, S O dot T. I'm saying O dot because I can see that that's the LaTeX symbol for it when I hover over it. The backpropagation algorithm is based on common linear algebraic operations, things like vector addition, multiplying a vector by a matrix, and so on. But one of the operations is a little less commonly used. In particular, suppose S and T are two vectors of the same dimension. Then we use S O dot T to denote the element-wise product of the two vectors. Thus, the components of S O dot T are just S O dot T of J is equal to Sj times Tj. As an example, you 1 times 3 and 2 times 4, and that gives you O dot with a Hadamard product. This kind of element-wise multiplication is sometimes called the Hadamard product or Schur product. We'll refer to it as the Hadamard product. Good matrix libraries usually provide fast implementation of the Hadamard product, and that comes in handy when implementing backpropagation. Okay. The 4 fundamental equations behind backpropagation. Actually, just like while we're here, how do you do NumPy Hadamard product? Oh, that's what times does. So that's what I was accidentally doing earlier. Interesting. Good. Backpropagation is about understanding how changing the weights and biases in a network changes the cost function. Ultimately, this means computing the partial derivatives, derivative of C with respect to WLJK and derivative of C with respect to VLJ. But to compute those, we first introduce an intermediate quantity, delta Lj, which we call the error in the jth neuron in the Lth layer. Backpropagation will give us a procedure to compute the error delta Lj, and then we'll relate delta Lj to derivative of C with respect to WLJK and derivative of C with respect to VLJ. To understand how the error is defined, imagine there is a daemon in our neural network. Neuron J, layer L. The daemon sits at the jth neuron in layer L. As the input to the neuron comes in, the daemon messes with the neuron's operation. It adds a little change, delta ZLJ, to the neuron's weighted input, so that instead of outputting sigmoid ZLJ, sigmoid of ZLJ, the neuron instead outputs sigmoid of ZLJ plus delta ZLJ. This change propagates through the layers in the network, finally causing the overall cost to change by an amount. Derivative of C with respect to ZLJ times delta ZLJ. The overall cost changes by this because Yeah, because you're saying the slope in the direction of ZLJ times the amount we moved in the direction of ZLJ. Okay. Now this daemon is a good daemon and is trying to help you improve the cost, i.e. they're trying to find a delta ZLJ which makes the cost smaller. Suppose derivative of C with respect to CLJ has a large value, either positive or negative. Then the daemon can lower the cost quite a bit by choosing delta ZLJ to have the opposite sign to derivative of C with respect to ZLJ. By contrast, if derivative of C with respect to ZLJ is close to 0, then the daemon can't improve the cost much at all by perturbing the weighted input ZLJ. So far as the daemon can tell, the neuron is already pretty near optimal, and so there's a heuristic sense in which derivative of C with respect to ZLJ is a measure of the error in the neuron. As a footnote. This is only the case for small changes delta ZLJ, of course. We'll assume that the daemon is constrained to make such small changes. Okay. Okay, so for each neuron, if you can calculate the slope of the cost function with respect to the weighted input to the neuron, then you can tell how important is this neuron to the cost. If it's low, then it's not that important. That means like you can change it a little and it's not going to change the cost very much. If it's high, then it's very important. Because then when you change, because the cost changes by this amount, so if this number is big, then this number will be big. Okay. Motivated by this story, we define the error delta LJ of neuron J in layer L by delta LJ is defined as derivative of C with respect to CLJ. Okay, so the slope of the cost function with respect to the weighted input is what we're going to call delta LJ. As per our usual conventions, we use delta LJ to denote the vector of errors associated with layer L. Backpropagation will give us a way of computing delta L for every layer and then relating those errors to the quantities of real interest, derivative of C with respect to WLJK, and derivative of C with respect to BLJ. You might wonder why the daemon is changing the weighted input BLJ. Surely it would be more natural to imagine the daemon changing the output activation ALJ, with the result that we'd be using derivative of C with respect to ALJ as our measure of error. In fact, if you do this, things work out quite similarly to the discussion below, but it turns out to make the presentation of backpropagation a little more algebraically complicated. So we'll stick with delta LJ equals derivative of C with respect to CLJ as our measure of error. Footnote. In classification problems like MNIST, the term error is sometimes used to mean the classification failure rate, e.g. if the neural net correctly classifies 96.0% of the digits, then the error is 4.0%. Obviously, this has quite a different meaning from our delta vectors. In practice, you shouldn't have much trouble telling which meaning is intended in any given usage. Okay, plan of attack. I already know the plan of attack. It's figure out a way to calculate the partial derivatives of the cost function with respect to the weighted inputs, and then use that to figure out the partial derivatives of the cost function with respect to the weights and biases, and then use that to figure out how much we should be moving. No, we already know how much we should be moving. Use that to figure out in which direction we should be moving by the learning rate amount in order to minimize the cost function. Okay, plan of attack. Backpropagation is based around 4 fundamental equations. Together, those equations give us a way of computing both the error, delta L, and the gradient of the cost function. I state the 4 equations below. Be warned, though, you shouldn't expect to instantaneously assimilate the equation. We'll see about that. Such an expectation will lead to disappointment. We'll see about that. In fact, backpropagation equations are so rich that understanding them well requires considerable time and patience as you gradually delve deeper into the equation. The good news is that such patience is repaid many times over, and so the discussion in this section is merely a beginning, helping you on the way to a thorough understanding of the equations. Here's a preview of the ways we'll delve more deeply into the equations later in the chapter. I'll give a short proof of the equations, which helps explain why they are true. We'll restate the equations in algebraic form as pseudocode, and see how pseudocode can be implemented as real running Python code. And in the final section of the chapter, we'll develop an intuitive picture of what the backpropagation algorithm equations mean, and how someone might discover them from scratch. Along the way, we'll return repeatedly to the 4 fundamental equations, and as you deepen your understanding, those equations will come to seem comfortable and perhaps even beautiful and natural. An equation for the error in the output layer, delta L. The components of delta L are given by delta uppercase L, which is the error in the output layer, are given by delta L of j, delta Lj, so the error in the output layer of the jth neuron, is equal to the derivative of the cost function with respect to the output activation for j times the derivative of the sigmoid function of the weighted input of j. That makes sense. Because this is just like the definition of the derivative, of a partial derivative, really. This is a very natural expression. The first term on the right, derivative of c with respect to ALJ, just measures how fast the cost is changing as a function of the jth output activation. If, for example, AC or C doesn't depend much on a particular output neuron, J, then delta Lj will be small, which is what we'd expect. The second term on the right, sigmoid prime ZLJ, measures how fast the activation function sigmoid is changing at ZLJ. So the definition of this is derivative of C with respect to Z? Is that how delta was defined? Yeah, with respect to Z. So we're saying derivative of C with respect to Z is equal to okay, I guess I am a little confused about this. Why isn't it only equal to sigmoid prime of Z? Oh, because that would be the derivative of A. That would be the derivative of A with respect to Z. So that's why this makes sense. The derivative of C with respect to Z is equal to derivative of C with respect to A times the derivative of A with respect to Z. And I don't know how to prove that other than with the trick of like the two things cancel out. about. I just remember from calculus that that's how that works. Like derivative, like del L or del of A is in the denominator here, and it would be in the numerator up here. Which is not a proof, but it's just like a way to remember this rule. Okay. Notice that everything in BP1 is easily computed. Okay, if it's easily computed, then let's compute it. So delta L, so delta of the last layer, is equal to I don't know what to call this, but like grad CA times sigmoid prime of Z of the L. Okay. Sigmoid prime. I might just have to look up. It's the derivative of, like, where's my sigmoid function? Sigmoid function is here. So let's add that over here. Oh, we've already got it. Let's add sigmoid prime. And I don't know how to do that. I just have to look that up. Derivative of sigmoid. Is equal to sigmoid of Z times 1 minus sigmoid of Z. Okay. This should be np.nb array because we want to do it, we want to vectorize it. Okay. So sigmoid prime of ZL. How do I know ZL? Z is the weighted input to the last layer. So if I just did the forward propagation and then I remembered the last layer, that would be ZL. So let's do a forward propagation. This is not the right thing to copy. It's not how you do a forward propagation. I just want to find my apply function. So why don't we start with A equals X, because I don't want to lose X. Actually, I don't think I care about X anymore, so let's just do it like this. The final X is the output, so this is A of L. The thing I want is the final one of these. So let's call this Z. And now ZL is this, the final Z. It's underlined. Z is possibly unbound. That's true, because how about this? Z's equals a list. Z's.append Z. Take the last one. This is a list of np.np arrays. But I don't know. I don't know how to calculate this value. Derivative of the cost function with respect to A. I guess I do know how to calculate that because the cost function is this, right? C is equal to A minus, or this is X because it's the last A. I can do the same thing. X is equals, this is a list of these. X is dot append X. So C is the last X minus Y. This is vectorized Y, so I haven't defined vectorized, but it's but I'll be able to do that easily. So it's this squared, right? This is C. We're saying Y is a constant. This is a variable. So we're saying, what's the derivative of C with respect to this? The answer is going to be two times this. We have to distribute the square here. So it's this times this. Which is equal to this squared minus 2 times this times this plus this squared, right? Where this is a Hadamard product. So the derivative of that is 2 times this minus 2 times this and then the constant goes away. Okay. How do you do vectorize y? So let's go up here. Def vectorize goes to an NP array. I guess I have to know that it needs to be 10 things big. So ret equals np dot zeros 10. Ret of y equals 1. Return ret. I guess I see why this was done as part of the data loading, because this is not really part of the neural network. This is just part of the thing that we're training. So I guess I will change my mind here and return label will be an array as well. Which means I'm not just converting these to lists, I'm vectorizing these. Vectorize label or label then let's move vectorize from here to there. This should be np.nparray. Then we have to change a few things. So first of all, we don't need to vectorize y anymore, it's already vectorized. But that does mean we have to change this to argmax this as well. Argmax both sides of that, because Python import numpy as np.array, let's say it's 0, 0, 1, 0. If we take np.argmax, we want this to say 0, 1, 2. And it does. So that is what we want. Okay, so we figured out how to calculate it. Good job, or how to calculate just delta L. Notice that everything in BP1 is easily computed. In particular, we compute ZLJ while computing the behavior of the network, and it's only a small additional overhead to compute sigmoid prime of ZLJ. The exact form of derivative of C with respect to ALJ will, of course, depend on the form of the cost function. However, provided the cost function is known, there should be little trouble computing derivative of C with respect to ALJ. For example, if we're using the quadratic cost function, then C equals 1/2 times sum over y of j minus a of y minus a squared, and so derivative of C with respect to a is going to be equal to a minus y. I forgot that there was the half in the cost function, so that means I can get rid of the 2 times and the 2 times, because this whole thing is 1/2 times this. I guess I see why there's the half in the cost function then, so that the derivative is easy to work with. Which obviously is easily computable. Equation BP1 is a component-wise expression for delta L. It's a perfectly good expression, but not the matrix-based form we want for backpropagation. However, it's easy to rewrite the equation in matrix-based form as, yeah, that's already what I did, because this star here is the Hadamard product, the BP1A. Here, grad of AC is defined to be a vector whose components are the partial derivatives of C with respect to A. You can think of grad of AC as expressing the rate of change of C with respect to the output activations. It's easy to see that equations BP1A and BP1 are equivalent, and for that reason, from now on, we'll use BP1 interchangeably to refer to both equations. As an example, in the case of the quadratic cost, we have grad of AC equals A minus Y, and so the fully matrix-based form of BP1 becomes delta L equals AL minus Y, Hadamard product, sigmoid prime of DL. Yes, that is what we're doing. As you can see, everything in this expression has a nice vector form and is easily computed using a library such as NumPy. An equation for the error delta L in terms of the error in the next layer, delta L plus 1, in particular. Delta L equals the weight of the next layer transposed times delta of the next layer, Hadamard product sigmoid of the activation of this layer. No, the weighted input of this layer. Can you tell why that's true? No, I can't tell why that's true. I think I'll have to just keep reading. I mean, I know it's something like this is the derivative of this sigmoid. So this is the derivative of A of this layer with respect to Z. Which means I know this is going to have to be the derivative of the cost function with respect to A. But I guess I don't see why this is how you figure out the cost function with respect to A of this layer. Where W of L plus 1 transposed is the transpose of the weight matrix W of L plus 1 for the L plus 1th layer. This equation appears complicated, but each element has a nice interpretation. Suppose we know the error delta L plus 1 at the L plus 1th layer. When we apply the transpose weight matrix, WL plus 1 transpose, we can think intuitively of this as moving the error backwards through the network, giving us some sort of measure of the error at the output of the ith layer. We then take the Hadamard product with sigmoid prime of Z of this layer. This moves the error backwards through the activation function in layer L, giving us the error delta L in the weighted input to layer L. By combining BP2 with BP1, we can compute the error delta L for any layer of the network. Okay, I mean, I don't really get this, honestly. I don't know if I'm supposed to really get it yet. I only kind of get it in the way that it's like, you know, I'm kind of moving the error backwards in the network, but I don't really get it. By combining BP2 with BP1, we can compute the error delta L for any layer in the network. We start by computing BP1 to compute delta of the final L, then apply equation BP2 to compute delta of L minus 1, then equation BP2 again to compute delta L minus 2, and so on all the way back through the network. Okay, we can do that. So this is the final delta L. Why don't we yeah, so that's the final delta L, and then let's make deltas be a list of ND arrays, and it can start with this delta L. Then we'll insert to the front of it repeatedly. So we only need the weights, right? Isn't that weird? We only need the weights. So for W in self.weights, we want to go through them backwards. So reverse. Deltas dot insert at 0. I don't like that. That's hard for me to understand. So I'm just going to say deltas equals something plus deltas, and this something is going to be the delta for this layer, which is, actually I can even use this syntax, delta, comma, star deltas. This is like the JavaScript style list destructuring syntax. Okay, so delta is the transpose of W, so W dot T, multiplied by the previous delta, so deltas of 0, because we're building the list backwards. No, not multiplied. This is a matrix multiplication, and then you take the result of that, and you Hadamard transform, or Hadamard, what am I trying to say? Hadamard product this with sigmoid prime of now I have all of the z's, but I need to have an index here. So here I should do for IW in reverse of enumerate weights. Why doesn't it like that? You can't reverse and enumerate. Well, that's annoying. I guess I can enumerate, and then I just need to know that I want the opposite of this, so len of self.weights minus I. I hate that. Let's call that L. Yeah, that's it. That gives me all the deltas. If I've removed all my off by one errors, which I'm sure I haven't, but I guess we'll find that out as soon as we run it for the first time. Okay, then BP3 an equation for the rate of change of the cost with respect to any bias in the network. So this is what we were looking for. This is one of the outputs of the backprop. Yeah, this is this. Deltas is that. So we're going to be returning something and then deltas. That is, the error delta LJ is exactly equal to the rate of change C with respect to B. This is great news since BP1 and BP2 have already told us how to compute delta LJ. We can rewrite BP3 in shorthand as delta C over B equals delta. Where it is understood that delta is being evaluated at the same neuron as the bias B. An equation for the rate of change of the cost with respect to any weight in the network. In particular, the rate of change of the cost with respect to W is activation of the previous layer, Hadamard product. I think this is a Hadamard product. It doesn't have the symbol, but you're multiplying two vectors. Oh, I guess at this point it's not a Hadamard product because it's component-wise. Yeah, so this is just a number, but when you take them together, you'll take the Hadamard product, right? Written in a less, okay, this tells us how to compute the partial derivative C with respect to W LJK in terms of the quantities delta and A of L minus 1, which we already know how to compute. The equation can be rewritten in a less index heavy notation as derivative of C with respect to W is equal to A in times delta out. He dropped the Hadamard product notation, but I'm pretty sure there's a Hadamard product between these two. So let's compute these things. These grads of C with respect to W. Is C or is I called them so A in, so activation, which is X's for me. X of the previous layer, so let's do J minus 1. Hadamard product delta of the next layer, so J. So for J in range len of self dot weights. We're going to append these. We're going to define this as a list of e.nd arrays. And that's the other thing we're returning. Grad CW. What's wrong with this? Delta. Yes, because I mean deltas. Okay. Now I don't understand why VP3 and VP4 are true, but maybe we'll get to that. Where it's understood that A in is the activation of the neuron input to the weight W, and delta out is the error of the neuron output from weight W. Zooming in to look at just the weight W and the two neurons connected by that weight, we can depict this as derivative of C with respect to W equals A of in times delta out. A nice consequence of equation 32 is that when activation A in is small, A in approximately 0, the gradient term, derivative of C with respect to W, will also tend to be small. In this case, we'll say the weight learns slowly, meaning that it's not changing much during gradient descent. In other words, one consequence of BP4 is that weights output from low activation neurons learn slowly. There are other insights along these. So I understand that. The derivative of the cost function with respect to weights is equal to the activation of some neuron times the delta of that neuron. So if the activation is low, the rate will be low. So low activation neurons learn slowly. There are other insights along these lines which can be obtained from BP1 to BP4. Let's start by looking at the output layer. You know what? We can run this now. Let's try it. It's not gonna work, but we have what we need. Python main.py. When we vectorized y, we didn't reshape it. So should this be 10, 1? Doesn't like that. Ret dot, maybe over here, ret dot shape 10, 1. Y somehow doesn't have the right shape. One second. Y somehow doesn't have the right shape, which means somehow not vectorizing it properly. I'm not sure how it could end up without the right shape. This is during training. We're not using test data, we're just using training data. Mini batch is data. You can add types here. Why doesn't it like Y? Backprop thinks it's not an int anymore. Now it says data, and this is an image. Why doesn't it like that? Oh. Wait. This isn't a data. This is a label. So I can do for data label image. And then the problem is grad CA equals this minus Y. So I guess there's a few problems here. The first is that x's of -1 is supposed to be a 10 by 1, not a 10 by 30. The second problem is that sigmoid prime of z's of -1 is supposed to be a 10 by 1, not a 10 by nothing. So let's try one thing at a time. Did I print any shapes? Okay, this was so confusing. Red in power. Like, when did I write red in power? But okay, overflow encountered in power. Overflow encountered. Does that matter? That's just a warning. Somehow it never printed z.shape, did it? I don't. How did it never print z.shape? Oh, because sigmoid prime happens right after, not right before. Okay. Print me the xz's. Print me Y. I guess this is pretty hard to read. Okay, don't print me the xz's, just print me the shapes for each one. X.shape for x in this, and print me y.shape. 30, 30, 10, 30, 10, nothing. I don't get it. That's not right. Well, because the last X is supposed to be the output of the forward propagation. We're doing the same as in the forward prop, aren't we? Maybe that's not working. What if I don't train? What if I just validate? Does that work? It does, and I get 12.5% accuracy. And if I do it again, I should get some other random percent close to 10%. 0%, that's odd. Okay, I don't understand. Why would it be easier remotely? Alright, lots of things to try to figure out. So I guess the first thing I'm curious about is what am I curious about? This is the activation. Print a dot shape, then a. Let's kill that. I'm not seeing the shape. Why is there no shape? Oh, because it's a matrix, so this is all part of one of them. It's 10 by 30. Okay, our forward propagation is messed up. Okay, then let's not even try to propagate. Let's just do print net or w dot shape or w net dot weights. E or E five. Let's start with that. 30, 784. And 1030. That's not good. Then the biases 30 by 1 makes sense, and 10 by 1 makes sense. So I think the biases are right. Actually, the weights look right too now that I think about it. So you multiply this matrix by a vector of size 784 to get 30, a vector of size 30. Then you multiply this matrix by a vector of size 30 to get a vector of size 10. So the weights and biases actually look right. This looks right. Print, yeah, for each application, print me w.shape, x.shape, b.shape. Oh, but I'll have no application because I commented out the validation. So W is this. Okay, this is not good. This is not a, it needs to be by 1. So did we fail to vectorize something, or did something get unvectorized when it went into a sigmoid or something? No, 784 means it started not vectorized. But how can that be? Because I'm vectorizing them. And then I'm reshaping them. Ref.shape. They don't have the right shape, even though I'm reshaping them right here. Is that because I have to reassign it to ref? Oh my goodness. Okay. Let's try removing our print statements and seeing if stuff just works. So I'm not trying to train right now. I'm using a random network, and I should see around 10%, and that's around 10%. Good. Now let's train it. And surely there are no problems with my training code, right? There was only problems in my loading code. Oh, I predicted I might have off by 1 errors there. ZS of J. So one thing is I don't actually want to do the last weights, right? Because I started because I already have the last weights in my deltas. So can I just do a -1 without thinking too hard about how to not be off by 1? That doesn't usually work, but let's see. Oh, interesting. So I think that means this has to be the way to do it. It's just that I have to not do the first one. How do you do that? You put the enumerate back here. Or I want to not do the last one, which means I have to change the way I'm doing my enumerate reverse thing, which I wanted to change anyway because it sucks. Well, I can just not include the last one, which might work, but it's still horrible. I don't know if that works. Let's just try to rewrite this. So I want to iterate backwards over the weights. Maybe instead of trying to do that, I can just do for I in range len of self.weights. I'm trying to iterate backwards, so I should be able to do reverse of this. I don't need this anymore. I can do J. What is W? W is equal to self.weights of J. But these are not the same layer, right? So I need them to be... Let's look at the formula here. I want the formula for delta. W of J plus 1 transpose. I'm already doing the transposing here. Hadamard product. Deltas of L plus 1. That's this because I'm going through them backwards. The list of deltas doesn't already exist, so I can't index it as J plus 1, I have to index it as 0. Okay. Any chance that And then I want to not do all of them. So len minus 1. This is a new error, so we got past that part. So now let's look at how to calculate gradient of C with respect to W. I'm guessing this is doing the negative indexing, which I don't want. I actually want this range to start at 1. It's the same error somehow. Oh, I think this is supposed to count the input. Which I'm not doing. Should I start X in here and then append? When am I using X's? I'm using the last one, which is okay, and then here's the only place where I index it by an amount. So maybe this can work. This is the input and this is the output. So I'm really doing this backwards somehow. How did I end up with 10-1 as the... Oh. I am not sure. Let's try to print some stuff. Print XS of J. I don't want to print. Print X dot shape for X in X's, and also print D.shape for D in deltas. So these are the X's. It starts with the input and then the activations of the second layer and then the activations of the final layer. My deltas start one to the right, which makes sense. So I think the right way to say this is your J and your J how do I say this? So that you're matching. So I want to skip the first one in X's, which is interesting because that's what it would have been if I didn't include the first one. So let's not include the first one. And then here we can just do this. We don't even need to do an offset. Which is messed up because now my indexes are not the same as in this code. Or as in this math here, equation. Okay, after all that training, we got to 13%. Is that expected? I mean, what was the amounts that they said you should be able to get? So this looks good. What were the hyperparameters there? 30 epochs. Mini batch size 10, data 3. I have a feeling we're not going to get the same results. I probably need to start printing stuff. So inside train. I like the library Q, I forgot what it's called, Python library progress bar. TQDM, let's use that. From TQDM or TQDM. And then you can just iterate over a TQDM of a range, and it'll work perfectly. So in the training here, for blank in TQDM, range epochs. And then I'm going to cancel this, clear, pip install TQDM. So epoch 2 of 30, 3. All right, it's gonna take a few minutes. I mean, these overflows are worrisome. Like, that might be the reason why I'm not learning. So try to figure that out. So I'm using POW, which is a built-in Python way to take an exponential, but I could be using NumPy's exponential thing. So I'll try that once this is done. Yeah, we didn't learn anything. So let's do np.exp just to make it faster, 10 epochs. I would also like to implement the thing that shows me the learning as we go. We're already getting overflow. How did he do it? I'm pretty sure I saw np.act. Yeah, literally the same thing as us, right? Yeah. And we did not learn. Sigmoid overflow. Save me stack overflow. Although, like, this actually shouldn't matter because he didn't have, if he's using this, then that can't be our problem. But what could be our problem then? Because what else would make it run but not learn? This is not going to be easy to figure out. Oh, maybe maybe I'm not doing this part properly. But the fact that the shapes are right makes me wonder how I could not be doing it properly. Okay, let's compare to their code. So here's train. Shuffle. It's also what we do. Then we're iterating over mini batches of a certain size. We're calling update mini batch with Ada. They're also, after each epoch, evaluating. Did I make a dot evaluate? I made a validate. What are they evaluating on? Oh, if you pass in test data. Okay, well we could try that. If test data self dot validate test data. Multiply that by 100 and add a percent symbol on the end. there's a better Python way to do this. Python print percent. Oh, no, I still need the times 100. So here I could do colon 0.2%. Why do you put the percent inside that? I'm not sure, but let's see what this says. Well, wait, I didn't pass in test data, so it won't do anything. Test data equals test data. Or data dot tested. So now it should forward propagate after every epoch to see how well we're doing. Oh. Wait, so I'm not supposed to do the times 100 if I'm going to do the percent thing. Clear that. Try this. Where's that first print coming from? I'm not really learning, yeah, I'm just staying around 12%. Like, interestingly, I'm learning a tiny bit. But then I plateau at 12%, so maybe it's a coincidence. So, what else could it be? I guess let's keep reading. Update mini batch. There's a decent chance I'm making a mistake here. So nabla B, nabla W. I'm calling those grad B and grad W. For XY and mini batch, that's the same. So all the way up to here, we're the same. Here we're also the same, but they're calling delta nabla B what I'm calling delta grad B. And here they're doing it in list comprehensions, and I'm doing it iteratively. But let's be certain that we're doing the same thing. So they're doing nabla B, which starts as zeros, is equal to then we're iterating over the things in nabla B, so that's the same as iterating over the length of the weights, because there's that many. There's the same number of weights and biases, and then they're saying for each of those, these are vectors, and these are matrices. For each of those things, ND arrays, the new value is equal to the old value plus the delta. And that's also what I'm doing, just in an easier way to read, I think. And then at the end, they say the new weights is equal to the old weights. So we're iterating over the length of weights. So the old W minus eta over length of mini batch nabla W, which for me I'm calling grad of W. So I seem to be doing the same thing. Now let's take a look at backprop. Backprop. So they're declaring the things they're going to return at the top, and then they return them at the bottom. Nabla B, Nabla W. I don't declare them explicitly. Well, the grad C with respect to W I do. And this I called delta grad W before. Yeah. But it's the same thing. Okay, so they start them as zeros of the right shape. Then activations starts at X. I had this for a bit, and then I got rid of it because I ended up not needing the first one. So they've got the Z's and the activations. I have the Z's and the activations. For the weights and biases, Z is equal to W matrix multiplied by activation plus B. That's what I'm doing. Then you add that to the list of Z's. Then you sigmoid it. Then you add that to the list of activations. Okay. Then our starting delta is self.cost derivative of activation of the last activation, so that's this, and Y. And I'm guessing cost derivative is just going to be the first thing minus the second thing. Yeah. Okay, times sigmoid prime of the last Z. Times sigmoid prime of the last Z. Okay? So far we're doing the same thing. Here's where the indexes will start to get different for us because I'm building the delta list as I go instead of filling it in. Starting with the zeroed out matrix. So the last thing in each of them, delta for one, and it's actually this is interesting. So delta makes sense for one. I'm going to just return my list of deltas, and so the last one will be there. The last W, I don't start by defining the last W, I just compute all the W's the same way. That means I'm probably missing the last W. I might be missing the last W. No, I don't think so. I think I'm still getting them all, because I'm iterating over all of the weights here. So I don't think I'm missing any W's. He's doing a dot product between delta, so the last delta, which is what this will be once we're at the last J. And the last activation. Well, activation minus 2. The before last activation. Um, So this would be the last activation if they didn't start activations with X. No, that's not true. Okay. So maybe you do need to start it with X. And I should be doing -1 here. And starting you at 1. I don't know. I'm just doing random stuff. Like, the thing is, all of the sizes matched here, which is really hard to imagine that they would do. Print grad CW, print g.shape for g in this, print d.shape for d. Also print w dot shape for w in self dot weights, and b for b in sizes. Okay, that's not what I expected. This isn't quite right. I don't know which one's which, so let's add weights. That'll be enough. That'll let me know. Okay. So my grad C of W is actually not the right shapes. Yeah, because weights these are the matrix sizes of the weights. My grads should be the same shapes as my weights, because I'm going to use them to modify my weights. So this is wrong. This guy, I'm not getting the right answer for this guy. I am getting vectors, but I should be getting matrices. So why don't you print xs.j.shape deltas of j dot shape. And they are always vectors, which actually makes sense. And I guess that's why here they're transposing it. I completely missed that we were... that this was turning into a matrix. Like, activations is a vector, delta is a vector. It doesn't specifically say that what you're supposed to do here is transpose one of them and turn the result into a matrix. I just missed that. I didn't realize that's what we were supposed to do. I wonder if it matters which one gets transposed. Operands could not be broadcast together with shapes 30, 780. Why is there 3 here? Oh, probably just because this is the result it was trying to make, and this is the input. Alright, let's print. Here we might need the x's again. Print me. Yeah, because now we want the outer products of x's and deltas. So why don't you start here and you start there, which is how we thought it should work. But it wasn't working before, we were doing the wrong operation. Okay, how about this? Print. X.shape for x and x's. And then raise. Print D.shape for D in deltas. And print W for W in self dot weights, and we'll just figure out based on that what's supposed to be outer producted with what. Oh, you know what? This needs to be an at if this is going to be matrix multiplication now. So what we want to end up with is 30 is a vector that's 30 by 784, which means if you transpose this, you get 1 by 30. If you multiply this by that, so I think this will actually already work with this little fix here using the at. Let's see. To do matrix multiplication instead of a dot product. Or a Hadamard product. I forgot to remove the radius. Wait. Print me these again, and then just raise, like, whatever. Alright, here I'm starting at 1, but I don't actually want to do that, I think. So, yeah, I want the first of these and the first of these, and then the first of these and the first of these, and then I don't care about the last. X. So don't start at 1. but also don't do -1. By 784 is one of them, and 784 by 30 is the other. So I think that just means we want to do the other way around somehow. Is this what will do that? No, this will just give a number, won't it? If I do .t here, and then I put this on the other side. Okay, I'm really having trouble here. Like, this was really close. It's just that it was transposed of what it needed to be, right? I don't know if this makes any sense. I'll have to, like, try to understand why we're taking these outer products, I think. But we're not getting exceptions, and we're learning. We're at 21% digit classification, and we stopped learning. We're down to 16. We're getting dumber. We're doing good for a sec for the first epoch. Oh wait, we jumped back up. Maybe it's just random. 36. Okay, we're learning. All the way back down. I mean, it did better than before. I'm not confident that this does what I want to do. So how are they? Where is it? How did they implement that part? So they did deltas. Dot product did with this dot transpose, which I thought would be the same as what I was doing, or at least would give the right dimensions, but I thought I tried this and it didn't work. I guess it does work. And like again, a big jump in accuracy in the first epoch and then back down. Really weird. What were the numbers that he said worked really well? 30 epochs, 10 3.0. I mean, that's almost what we're doing. So I don't give a lot of hope that just adding more epochs is going to work. Yeah, after one epoch, it should already be extremely good. So the problem's not the number of epochs. So let's stop that. What else are we doing differently? So there, he's also skipping the first layer, but that's also because he added it already on the outside. And we're doing it in 2 separate loops, so we don't have to worry about the extra W the way he does. Negative L plus 1. He's using negative indexing into the list in order to fill the list out backwards. I don't have to fill this list out backwards because the things don't depend on anything that I don't already have. This one I do have to fill out backwards. So I'm getting the 1 at j plus 1. Which is the same as what he's doing, just with I'm indexing it in a different way. Take the transpose, multiply that by delta, which is the last delta. That's how he's doing it, is he's just remembering the last delta. That's the same as what we're doing by just getting the first delta in our list of deltas, which will be the last delta. And multiply that by sigmoid prime of z, which is the current z, which is what we're doing too. We add that to the front of our list of deltas. So this seems to be the same, the delta calculation. Okay. What else could I be doing wrong? I guess, what about the first nabla W, which I call grad CW? So that's going to be at delta of 0. Which will be the first delta at 0 will be the first delta in my list. Keep doesn't keep track of deltas, right? But this is the last delta. Oh yeah, because, okay, so -1 here is the last W, so I should look at the last J. So at the last J, this will be the last delta, which is delta L. So this is the same thing for us both. The last nabla W will start with delta L times the activations from 2 before, which actually means the before last activations, because -1 would be the last one. The before last activation. So when J is at the end of the list of weights, there's still going to be 1 activation left. So that's the same as what I'm doing here. So this all seems like I'm doing the right thing. Therefore, there's no bug, therefore it's learning fast. The end. Sigmoid prime, right? Sigmoid z times 1 minus sigmoid z. I don't think I'm just bad at checking if I was right either, because that would, because then I wouldn't expect to start with a 10% classification ability. Okay, one more idea I have is that my pixels are starting from 0 and going to 255, and I don't know how his pixels work. Is that in here? I don't know if that matters. But we can try changing it. So you just divide that by 255, right? No way, that was actually it. Okay. Wow. Why would that matter? Maybe it just messes up the hyperparameters, where like I would need my eta to be bigger or maybe smaller if the inputs are going to start so big. Let's try that. So let's go back here. Let's say eta is 3 times 255. So way bigger because the inputs are way bigger. No, that's not helping. What about divided by 255? Way smaller because the inputs are way bigger. Well, it's not as good as before. It does seem to at least be learning at all. It's actually like going up over time. Okay, so I have a guess actually of what's happening. The first layer, its activations can be up to 255, so it needs a faster learning rate, whereas the other layers would need a slower learning rate. If I make sure that the input is scaled to between 0 and 1, same as the output of a sigmoid, of all the other sigmoids, then I can scale them at the same rate. I'm guessing there's something like that happening. So let's go to the data loader, let's divide it by 255. Let's be really thankful that I just happened to think of that before wasting too much more time. And then I really want to figure out where is this stupid print coming from. I don't know why I have not found that yet. Data loader, print. It is in data loader. Okay. Well, look at that. We built a neural network that can classify handwritten digits with a 94% accuracy and 39 seconds of training. Not too shabby. Yeah. The thing is, BP1 to BP4 are the only things that I don't quite understand. I do understand BP1, actually. BP1 makes sense. BP2 to BP4, I don't have a full grasp of yet. I understand the equation. I don't understand why it's right fully. Print f of percent colon 0.2%. Final accuracy. Why did I spell final like that? Why did I spell accuracy like that? So we can do this to do now. Train a network with just 2 layers. So just like that. What do you get? It's not going to be as good because it doesn't have a hidden layer to classify like bigger concepts. It can only look directly at the pixels and try to figure out patterns. It's not horrible though. 75% accuracy, like that's pretty good. And then if I did more epochs, it seemed like it was still learning. So, oh wow, we got lucky at the beginning there, and we jumped right to 80%. Okay, so what accuracy can you achieve? It's not as good, but it's not as horrible as you might expect. That's the answer. 83%, and it's still going up, so maybe you could get all the way to 90%. whereas the one with the hidden layers basically starts at 90% and then keeps getting better. Okay, let's end it there for the day. Thanks for watching.